So today we'll be seeing about the context-free grammar and its language. So we'll see how context-free grammar is generated from a language, because in the last session we have seen about how language is generated from context-free grammar. Now we will be seeing about how grammar is generated from the language. So that is the example we are going to see here. Then we will be seeing about what is context-free language, how derivation for the grammar is done. So we will be discussing about leftmost derivation and rightmost derivation. So we will see the examples for those things. So what is context-free grammar first? So context-free grammar is a finite set of variables and each of which will represent a language. So here the language will be described using two terms. One is terminal symbols and a non-terminal symbols, and you will have a set of rules called productions. So what do you mean by a production? The production states the language associated with the given variable contains the string that are formed by concatenation. Okay, so you will be possibly having with some terminal symbols. So that is CFG. So how do the context-free grammar differs from regular grammar? So your regular grammar is, you will have a restriction on non-terminals on both the left-hand side and right-hand side of the production. So on the left-hand side, in a regular grammar, there should be only one symbol, and that symbol also should be a terminal one in regular grammar. Whereas in the right-hand side, it may contain 0 or more terminal symbols. But if a non-terminal is present in the right-hand side, then it should be either leftmost symbol or the rightmost symbol. So these many restrictions we have with the regular grammar. But when you consider the context-free grammar, there is one and only restriction we have. So LHS should have a single non-terminal. That is the only restriction we have in CFG. Other than that, there is no restriction on the right-hand side of the production. You can have any number of terminal and non-terminal symbols that can be present on the right-hand side of the production. So how do we define the context-free grammar? Similar to the grammar, so a grammar will be consisting of V, T, P and S. V stands for non-terminal variable, non-terminal symbols or variable, and T stands for terminal symbols, P is for production rule, and S is the starting symbol. Okay, so in each and every production you know that it's a CFG. So alpha implies beta, means alpha should contain only the variables, only the terminal symbols, where beta can be, it's a union of terminal and non-terminal symbols. Okay, so the language will be generated, it should strictly follow with the end with the terminal symbols. It should not have any non-terminals in its string generation. So such language we call it as a context-free language, which is generated from the context-free grammar. So before going to the next topic of derivation of CFG and its language, we should know what is the application of CFG. So CFG is mainly used for parser tree construction and compiler design. It is mainly meant for syntax error checking. Okay, so syntax checking will be done using the CFG only. So CFG will provide you in which order or derivation tree the expression has to be evaluated. So that is the major advantage of context-free grammar. When you consider with the XML, it is mainly used for document type definitions. So multiple documents will be there, one and another will be related to each other. So whose data type has to be given to whom, that is perfectly given by the context-free grammar. So these are the two applications of context-free grammar here. Now let us see the derivation and its language using context-free grammar. So as I said before, if you are trying to derive from one term to the another term, that is to bring the final string, you will be making multiple derivations. So multiple production rule will be applied. For example, if you have A implies beta and you have any string like alpha and gamma, if alpha A gamma derives alpha beta gamma, then we may say that string alpha A y to obtain alpha beta y. So simple as, if beta 1 can derive beta 2 and beta 2 can derive beta 3 and beta 3 can derive beta n minus 1, n minus 1 can derive n, means we can simply say beta 1 can derive bn. So that is the derivation part we are doing, and with that derivation part we will say the given string w is accepted by the grammar or not. Okay, so that language will be generated from the context-free grammar is called context-free language. So if the grammar is context-free grammar. there are two types of derivations we have. One is leftmost derivation and another one is the rightmost derivation. So if the non-terminals are replaced with its derivation from left side to right side, then we call it as a leftmost derivation. If the same non-terminal, multiple non-terminals are available in the right hand side of the production and each non-terminals are derived to a terminal symbol from right side to the left side, then we will say it is a rightmost derivation. So we will see the example. You will get into clear picture what is LMD and RMD. We can go for the example now. Okay, today we will see an example. We will have an example for how to. So we'll write it over here. Construct CFG grammar to generate a set of palindrome. So you know what is palindrome is. Over the alphabet, A and B. So what is a palindrome? So when you read it from left to right or right to left, it should be same. For example, we'll take from the symbols, A can be a palindrome, B can be a palindrome, AA, BB, this everything can be a palindrome. So let us consider the combination ABA, AABAA, and other possibilities you can have BAB, again BBABB. Similarly, you can have multiple combinations. So this is the language that can be generated for a set of palindromes with the variable A and B. So which you can't have here is, you can't have AB because AB is not a palindrome. Okay, so it is not a palindrome. So how do we generate a CFG grammar for this? First you have to write the production rules. So let us have a starting variable s is equal to, we know that it can be also empty, so we will have empty, or we can have A or B. So you can have A or B. So this is the first rule we generated for with the first two string. Suppose if I need multiple A's or ABA, so what shall we do? If I need multiple A, so let us write the rule as ASA. So this will generate multiple A. If S is substituted with epsilon, then you can have AA. If you substitute again with the same pattern, you will have multiple A's for that. Similarly, I can write it for B also, SBB. So with this, I can substitute n number of possibilities. For example, let us consider that with this production rule, can we generate this string? So if I want to generate, first let me write S is equal to BST. Okay, then again instead of S I will substitute same thing, so BBSBT. Now instead of S I can substitute A, so I will substitute BBABB. So I am able to generate the string. So finally we can say our context free grammar G is equal to, so what are the variables we are using? Non-terminal variables we are using only S. So I am using only S. And what are the terminal variables? I have to use only A and B. What is the starting state? S. And what are the production rules? I can have S implies ASA or BSB or A or B or epsilon. So this is the context free grammar for the given problem. The next problem we are going to see here is, we are going to construct a CFG generating, you have to construct a context free grammar for the given language, 0 to the power of n, 1 to the power of 2n. So if n is 1, you will have single 0, then you will have 1 will be done. So let us generate the language first. So what is the question actually tells about? So the L of G is going to be, let us assume the n value is not going to be 0, so you don't have epsilon over here, it should be equal to 1. So when you substitute 1, it is going to be 0, 1, 1. When it is going to be 2, so you will have 0, 2, 2, 4 ones, and it goes on. So this is the language that is generated for the given formula. Now we have to write the production rule in order to generate the context-free grammar. So we'll write the production rule as, first thing, there is no epsilon. So if there is no epsilon, we always consider the exact string with the n value, with the initial value that should be considered. So we will consider 0, 1, 1 because that is to be done. So this 0, 1, 1, it is in the middle with here in the second operation. So we can write with that my second production rule can be 0 as 1, 1. Okay, so 0 as 1, 1. So that's all with this. If you want, you can try. Suppose if my n value is equal to 4, that means I will have 4 zeros and I will have 8 ones. So let us check whether with this production rule can I generate. So let me write 0s11 first. I will substitute for s alone again. So I will substitute 0, 0, s11, 11. Again for s I can substitute. So 0, 0, 0, s11, 11, 11. Okay. The last one I can substitute the exact string 0, 11 alone. So again here I am going to substitute 0, 11. So 0, 0, 0, 0. 11, 11, 11, 11. So I am able to generate for all types of string. Hence, the CFG grammar. One second. Okay, you can have the grammar. So the grammar G is going to be, so only one non-terminal variable, and you have 0 and 1 as a terminal variables. Your starting symbol is S. And your production rule is S tends to 0 S 11 or 0 11. So that's the given grammar for the generating the language 0 O of n and 1 to the power of 2 of n. The next problem is we have to construct a context-free grammar for a set of strings over A and B that is ending with A. Okay, so we'll see first what is the language that is generated for the grammar. So the language L, not for the grammar. Okay, it's the language generated. So the language generated is it has to end with A. So you can have A, but you can't have B. So you can have AA, BA. Then you can have any number of A's also. So you can have AAA, okay, or BAA, or BBAAA, or ABABA. Like this, I can form any number of strings. So let us start with the rule. So here it has to end with A. That means I can't have any empty string. So my starting symbol has to end with A. Similarly, when you take the second one, it has to be AA and BA. So I will write the rule as AS or BS. So instead of S, I can substitute A. So I need multiple A's as well as a multiple B ending with A or something like that. So you can take this one and this one as an example. So when you take that as an example, you can see ASA similarly or BS. So I hope we have derived everything. So suppose I want to derive this string. Can you derive with this set? We'll check. So S tends to, it is starting with B, so you'll have BSA. Now for S, I can substitute again BBSAA. Okay. Now I have to substitute one more A, so 2A. So instead of S, I can directly substitute A over here. So you will have BBAAA. So that is generated. Now if you want to generate this one, so let us assume S is equal to ASA. Okay. So instead of S, I can substitute ABS A. So instead I am using the second rule. Instead of S, I am substituting BS. Okay. Again, instead of S, I can substitute AS. So AB, AS, A. Then finally, instead of S, I am substituting only B. So AB, AB, A. So it is done. So your context-free grammar is going to be, it is S, only non-terminal variable, and your terminal variables are a and b, and your starting symbol is s, and your protection rule is s tends to a as a or b as a or as or bs or a. So this is the context free grammar for generating set of strings over a and b ending with a. Construct and CFG over the alphabets sigma is equal to a, b, open parenthesis, close parenthesis, plus star, dot and epsilon. So the summation symbol which represents the terminal symbols, so sometimes you may have epsilon also. So instead of that a summation symbol, we can take it as t also. So now we'll find out what is the first language is generated. So the language will be generated for the given problem is, it can be a star because it is the regular expression over a and b. So with these symbols I have to form a regular expression. So it can be of finite automata symbols. So a star, you can have a star b star, then you can have a plus b, a dot b, concatenation. Okay, then you can have a alone, b alone, epsilon. Then what is open parenthesis and close parenthesis? You can have a plus b, a dot b, and it goes on. So whatever the combinations you can write, you can write. So first we will start with a star and b star. So let us assume we are going to use this regular expression. So s is equal to s star. So then you can have ss anything. So we'll have s can be either a or b or epsilon. So it can be a star, b star, or it can be empty because we have epsilon also in our alphabet symbol. Next one is for a plus b. So I can write s plus s or s dot s, which can be written. Okay, so this is for these two operations. Then final operation is you can have a parenthesis. So that parenthesis can be either the summation or concatenation. So we'll write it like this. So open parenthesis and close parenthesis. So now we have written all the expressions. Suppose let us I want to know, have to write like this: a star plus b star dot a plus b. I want to write in this fashion, whether this string is accepted by this grammar or not. So we'll start with s tends to open bracket s. So instead of s I can substitute s plus s. So I will take s plus s open bracket. Okay. Okay. No. So we have to do it in the concatenation. So we'll just remove this. So we have an overall concatenation over here. So let me take s dot s first, then bracket s dot s. Okay. Then for this s, for this s and this s. So now s dot bracket s dot s. Then again instead of s I can have s plus s dot s dot s. Now I can have this one to be substituted. So s plus s dot s plus s. Now instead of s I can substitute s star. So s star plus s star dot s plus s. Okay. So finally you can have a star plus b star dot a plus b. So here the substitution I done it like what I can do. So it's my wish. So I substituted anything like that. Suppose if the substitution happens from left side onwards towards the right side, then we call it as leftmost derivation. Or if you start substituting from the right side towards left, then it is rightmost derivation. So okay, we'll have that in coming examples. Now what is the grammar generated over here is, so the grammar generated is, we have only one non-terminal and we have a, b, open parenthesis, close parenthesis, plus star, dot and epsilon are the symbols. My start symbol is s and my protection rule is s tends to open bracket s or s plus s or s dot s or s star, or it can be a, it can be b, or it can be epsilon. So this is my grammar that is generated for the given problem. Another example to construct the CFG for the given language. So first we'll generate the language. You can see AM, BN, then CP. So A M plus N should be equal to P. So we'll assume, let us assume if M and N are equal, so we'll take one, N is equal to 0. So if that is the case, AC. If M is 0, you will get BC. Okay, if M is 1, B is 1, what will be the term? So you will be having AB, C will be P is equal to M plus N should be the P. Okay, so M plus N should be equal to P. So P will be M is 1, B is 1, N is 1, so 2. So you will have 2 C's. Okay, now you will have 2 C's. So let us have 2A, B is 1. Then how many C's will have? So it is 2 plus 1, 3. So you will have 3 C's. Okay. So it's based on M value and N value. Suppose if A is 1, B is 2, then C will be triple C. So similarly, all the language will be generated. So there is no, you can see P is greater than or equal to 1 here. So P is greater than or equal to 1 means there is no epsilon. So we'll start with the language. So we'll take the first two symbols. It can be AC or BC. I can see BC here, I can see BC here. Sometimes you may have AC also. So in the last you are having AC. So we will take in that case, so S can be A of SC and B of SC. So why, sir? I can have many possibilities. See here, I can have multiple A's here, then with one BC here. So if multiple A means I have to repeatedly use A multiple times. So let us take this as an example. We'll see how it can be done. So AA, and you have 3A, 2B, then it means I have 5 C's. Okay, because M is equal to 3, N is equal to 2, then P will be 5. Now if that is the case, you take, first thing is we have A, so you will take ASC. So now again I will take ASC, C, and you have third as also, so you will take AAASCCC. So again I'm substituting the same thing. Now instead of S, I can substitute BC. Okay, so AAA, BSC, again triple C. One more C I need. Instead of one more BC I need, I can substitute this expression over here. So triple A, B, BC, then you have 4 C's, 1, 2, 3, 4. So you can see my string is accepted. So this is the grammar. So my CFG is going to be with only one non-terminal variable and 2 terminal variables, not 2, it's 3 terminal variables, A, B and C it is. So I'll rub this and write it clearly because it's A, B, C. My start symbol is S and my rule is S tends to ASC or BSC or AC or BC. There is no epsilon since this is my grammar. There is no epsilon because P is starting from N is equal to greater than or equal to 1. Let us quickly see what was the grammar that are generated for the given language. So for the first one, you can see what is the language it is generated. So it is starting with 0, so you can have an empty string. So we'll start substituting 1, 2, 3. Okay, so if N is equal to 1, it can be AB. So you will be having a string AB, then A square, B square, then it goes on. So the grammar you can write over here is, it is S tends to epsilon or ASB. Okay, so this is the grammar. So this is the production rule. So we can write that this is the production rule that is used for this language. Okay, so you know what is starting variable, what is terminal and non-terminals and all. So the only thing is, this is the production rule that is used for generating this language. Now the next one is, we are going to have N is greater than or equal to 1. So that means L will not have epsilon, only AB, A square, B square, then other things. So what will be your production rule is, you can have only AB or S tends to AB or the multiple times AB. So front and back should be A and B. So A, S, B. So this is the production rule when you have for greater than n. Now a little bit complicated. We'll go for that if n is even alone. So if it is n is even means you can have 0, 2, 4, 0. So you can have epsilon, you can have a square, b square, a4, b4, a6, b6, and it goes on. So this is the language. So now it can be 0. So starting symbol to epsilon. And next thing is I need a square b square, so a b b. Next thing is again plus 2 a's and 2 b's here, so let us have s here. So this is the production rule for the language when n is even. Suppose if it is odd means, okay, odd means you can have only a b alone, so the language will be generated as a b, a cube, b cube. Then you can have A6, B6, then A9, B9. It goes on. Okay, it goes on. So what you will do is, we don't have any, 0 is not an odd number, so you have to omit it. So S tends to AB, it's a single string. Similarly, when you add multiple things, you have to need A cube. So the second term you take it. So you will have 3 A's. Okay, and 3 b's, again plus 3 only because it's an odd number. So you can have, it's not an odd number. Okay, odd number means a3, it is 5, 7 something. Okay, you will be having a5, a7, a9, something like that. So plus 2 variables, only plus the difference between these two a's is 2 and b is 2. So you will have s, b, b. Okay, so the last one is multiples of 3. Okay, what is the language can be generated for multiples of 3 is 0 is a multiple of 3. You can have a3, b3 divisible by 3. Again a6, b6 divisible, a9, b9 divisible, and it goes on. So we have a 0. So my production rule will have epsilon. Next thing is you have 3 a's and 3 b's. Okay, I will have 3a and 3b. The second term also is having 6, so you have already 3 a's, so only another 3a has to substitute, so it's a recursive, so you will take s. So this is the production rule for the n is multiples of 3. Now we will take the same example an, bn, which is not a multiple of 3. So what will be the language that will be generated over here is, it's not a multiple, so it should be even numbers. So you will take L is equal to AB, A square, B square, A4, B4, okay, and which is not a multiple. 5 is not a multiple, so A5, B5. 6 is a multiple, where 7 is not a multiple, and 8 is not a multiple, so it goes on. So what can be the rule? There is no epsilon here because 0 is a multiple of 3, so we don't have. So you will have AB. Now here A, B and A, you have 2 A's here, so we will take the language A is, so we'll have AB here. No, we'll take it in a different fashion. So we'll give, first we'll take AB gives, okay, let me do one thing. I will write it over here. So let us have a new rule called A. So A will be A, A, B. Okay, so if this is A, A, B, A can be substituted with epsilon. Similarly, you can have, no. I'm confusing with the some other term. So AB means, so again you can write S is equal to AB. Then you can see it has multiple 2 A's, so you can have 2 A's here, so that cannot be generated. So you have A, S, B, so that can generate A square and B square. So all other things can be also generated over here. So that's the production rule for the first problem. So next one is AN, BN. So first you write it like AN, BM, BN, CM. So AN and BM are in this way. So you have to consider in such a way. So let us consider the language, what it is, it will be generated. If N alone exists, you will have AB. If M alone exists, you will have BC. Here N is 0, so you can have epsilon also. So 0. Then if N is 1, B is 2. Or if everything or 1 means you will have A, B square, C. Then you can have A, B cube, C square, and goes on. Okay. So first what you'll do is we'll have a separate rule, because when it goes, we don't know which M is substituted or N is substituted. So you'll have separate rule for M and N. So we'll take A is equal to epsilon. Okay, so if you take this AB, I need a substitution, so I'll have AB. So for the first AB I have done. Similarly, we can have for B, okay, epsilon. We can have BC, BC, because it's having another terminal we can have. So this can be multiple time, it can be substituted. So I will take my S is equal to AB. So here S is the starting symbol. So you'll write it over here. So you will so S is equal to A and B. Now if the same condition, when you are going, when N is greater than equal to 1 means what I have to do. So now the language will be generated as AB, BC, then A square C, A B cube C square, and it goes on. So what I have to do here is, so we'll have the same rule, S is equal to AB, but only thing is A has to be different. So we will take AB as an input and you will have AAB. Similarly, B can be, we will take the input with BC, and this can be again multiple time, it can be substituted with C. So this is the production rule for this problem. So now let us see what is the language generated for the 9th question. So it is starting from 0, greater than or equal to 0. So we will have epsilon. So this you can write like this: AN, BM, BM, CM. Okay, so it's AM, BM, CM. So let us assume, okay, only is there. So we can have AB. Okay, so if either N or M is 0, so AB, other is 1. Next one you can have is if both are 1 means you will have A square, B square. Similarly, you can have AC, AC square, 2 square. And what are the other things you can have is A square, BC, A cube, BC square, A cube, B square, C. So just substituting what is the value for N and M and other things. So now we have to generate. So we know we have a separate string for A, B and AC and everything. So we'll have similar way. So I will take A. So it can be epsilon or AAB. Okay. Similarly, I can take for B. So because we have AC over here, so epsilon ABC. Then what will be your starting symbol? S will be either A and B. So this is the rule for this problem. Okay. Next one is if it is starting with 1 means it is must that you don't have your language without AB, AC, then A square, B square, A square, C square. It goes on. Okay. So the same string what is in the above, but only thing is you will not have epsilon. So what has to be done over here is, okay, I will change a little bit here. Why do we have to use two variables? So let me write it in the fashion first. A is equal to the exact string AB or multiple times A and B substitution. So you will take A, B. Now we will combine this B and SB here. So I will take my S itself. So I will take S for ASC for multiple times of substitution of ASC. Then I can even have C also. So you will have AAC. Okay, AAC. So you can substitute ABO in the middle because it has to end with C. So S will always end with C. You can see S is ending with S with C, but in between it can have multiple A's or it can have multiple AB also. So we will have these two as thing. To make sure that how this term a cube b square c is substituted. So you can have a derivation tree or path tree, we may say. So we'll start with S. So I need a b square a cube b square c. So I will take a c. Now a can be again substituted as a b. Okay. So what you need is still is I have two A's here, one C is here, one B is here, and finally I can substitute A and B. That is the final substitution, this one. Okay. Now if you travel through this tree in the only the leaf node, okay, only through the leaf node, you can see the string is accepted or not. So how do I make the substitution? That is the way I am taking it. Okay. So you can see it is A square, B square, C. So this is the derivation tree. So with this derivation tree, we can say a string is accepted or not. So now let us consider an example for derivation. So consider the grammar is given. So you have a non-terminal variable E, and you have terminal symbols like plus, star, open parenthesis, close parenthesis, and ID. Your start symbol should be E, and the set of protection rule is given. So let us write the protection rule first separately. So E tends to ID, and E tends to open bracket E, then E tends to E plus E, then finally you can have star also. So E tends to E star E. So if you need, you can name it as rule number 1, 2, and 3, and 4. Okay, now we have to find whether this string is accepted or not. So ID plus ID, okay, and you have star ID. So now this is the case. So let us start with E. So I am going to start. So let me take E star E first. Then I take open bracket E. So only for this E I am substituting. So then in that I can take E plus E star E. So I am doing this in this fashion. Then you can have ID for first E, then you can have the next ID for that, ID star E, then you can substitute the final ID also. So ID plus ID star ID. Now we will take an example. So this substitution we call it as leftmost substitution. So this is an example of LMD. So what do you mean by LMD? We will see it shortly. So you can see the substitution happens only from the left side towards the right side. Okay, I have underlined that, right? Now I will give an example for a rightmost substitution. So see, you'll take E is equal to E plus E. So which rule? It is up to you. Now E is equal to E plus E. Okay, then you will have E plus E star E. Okay, E star E. Now we'll start substitution ID for that. Now ID, see which one is getting substituted. Star ID E plus ID star ID, then again ID plus ID star ID. So you can see for which E it is done here. For this one, always the rightmost is first replaced, then after it is replaced we are going for the towards the left. So this is an example for rightmost derivation. So now you are given with a grammar and you have been given with a string A, B, B, A, A. So you have to show how it is derived using LMD and RMD, that is leftmost derivation and rightmost derivation. So I have written the rules in this here. So let me start the mission. So starting symbol is S, as always we know that. So we'll have S tends to AAS. Okay. So now I need multiple AS. So we'll take the second rule because we are going to substitute the second rule over here. So I'm going to substitute using rule 2. So if I substitute rule 2, leftmost symbol means from the left, what is the first non-terminal we have? So it is going to be A. So I'll substitute something for that to have a repetition. So you will have A, S, B, A, again S. Okay, so this is based on the rule 2. Now again we have a non-terminal S. So I need two A's. So we can substitute that. So AA, BAS. Okay, so this one is based on the rule 3. Now scan from left side towards the right side. What is the next non-terminal you have is A. So you can have substitute AB here. So what you need is BAA. So I can substitute the fourth rule over here. So I will substitute the fourth rule. So I will have AA, BB, BA, S. Now finally S is there. I can substitute the third rule to check whether my string is accepted. So it will be accepted. So AA, BB, AA. So string is accepted. So we can see the substitution started from left side towards the right side. Let us check for RMD, that is the rightmost derivation. So we'll start with the symbol SAS. Okay, so now for the S I have to substitute. So I can again substitute AS. Okay, so I will substitute AS. Okay. Okay. See, if you have two A's, only two A's is allowed. So we don't have epsilon. So we can't substitute this one. We'll replace this. Okay, instead of S, I will substitute A alone here. So which rule? I use the rule number 3. Now instead of A, I need one more A before that. So we'll use the second rule. So if you use the second rule, A, S, B, A. Okay. So now from the rightmost means this is the rightmost non-terminal symbol A. So for this I can substitute BA because the ending symbol is BAA. So we'll use the rule number 4 over here. So it changes to ASB, BAA. Now only non-terminal available is S. I can substitute A alone. So we will take the third rule. So you substitute, it will become AABBAA. So string is substituted. So this is an example for leftmost and rightmost derivation for the given grammar. So we'll have an example. So now this is the grammar and you have to find whether the derived thing. So it is not LMD or RMD. You can choose any method. So I am going to use LMD. Okay, so we'll start with S. So AB. So I need 3 A's. So I will repeat the same rule again and again for 3 A's. So AAB again for this B. I'm substituting. So that is, I'm using the rule number 3 here. So you will be using this one. So BB. Okay, again I can use the same rule. So leftmost B. So you will have 3A and 3B. Now for this B, I will substitute B. So you will have AAA, B, BB. Now we will have this B has to be substituted. So I will substitute BS because you have A over here in between. So we'll do one thing. So we'll have AAAB. Okay, BSB. So you'll have being BSB. Now you need A. I can use the rule number AB here. So we'll use the first rule for S. So I'm going to use triple A, double B, then AB. Okay, so I'll be using A, B, B. So you have two B's, again triple B has to be done. I can use BS or whatever the term. So what you'll be using is, after substituting AB, you will substitute this. For this you will substitute the B. So I will start doing that. So A, B, B, A, B, then you have B. So the final B you can replace with you can do with the BS. So we will do with the BS over here. So here BS means it is again with the third rule only. So A, B, B, A, B. Instead of that, I'm going to use BS over here. So BS, right? Again, this S, it can be substituted with BA. So I need multiples of B. So what you will do is I will substitute here A, triple A, double B, A, double B. Now I'm going to use, instead of S, I'm going to use A here. So B, capital A. So A can tends to the final A. So finally the A will be transmitted as A, B, B, A, B, 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 A. So finally your string is accepted by the grammar. We'll see another example. So here the string is given, so we'll write the rule first. So S tends to AAS or A, and A tends to SB A or BA. So this is the rule. So we'll use the string. So we'll start from the S tends to AAS. We'll start with this now. So we'll start leftmost derivation again. So instead of A, we'll substitute, because we have multiple A's here. So what you will do is we'll substitute AS, B, A, S. So again for S, I can substitute A. So you will have two A's. So AA, BA, S. Now instead of this A, I can substitute BA. So AA, B, BA, it's small a, okay, BA. Yes, finally for this S, I can substitute A. So AA, BB, AA. So string is accepted. But what is the question has having? Construct a derivation tree for the given string. So how do you construct? So see the derivation form. With that we can form the derivation tree. So from the starting symbol, I have substituted A, S. Now for this A, I have substituted SBA. So substitute SBA. Now for this S, I have substituted A. So you will have A over here. And for this A, I have substituted BA. So I have substituted SBAS. Okay, so for this A, I have substituted BA. So you have BA over here. And for this S, so let me have a little bit over there. Okay, so this S, it is substituted with finally with A. So you have a finally with A. So when you travel in the bottom leaves alone, you can find it is accepted. So if you see, it is coming from this direction to this direction, then to this direction. So it is A, B, B, again A. Only leaf nodes. If you travel, then it's giving the given string. So that's how we construct the derivation tree for the given string. So here the example is, we are given two symbols here, A and B. Okay, so it is, so yes, A and B are non-terminal variables and 0 and 1 are terminal variables. So two strings have been given here, 0, 1, 1, 0. I have to solve using RMD, and second string is using LMD, that is leftmost derivation. So first we will see RMD. We'll start with the starting symbol. S tends to 0, P. Now instead of B, what I can substitute here is I have 1, so you can substitute 1s. Okay, so 1s is there. Again I can substitute 1s, so you can have 0 1 1s. Then finally instead of s I can substitute here it is, instead of that I can substitute, instead of yes I can substitute 1a. That's wrongly written. Then instead of a I can substitute 0, so it is 0 1 1 0. So this one is based on the rule number 3, and this is based on rule number 1, and this is based on rule number 2. So your string is accepted. Now we'll come for the second string. So s tends to 0b, so using the first rule, because s is the starting symbol. Now instead of b I can substitute the third rule, 0bb. So I will substitute 0 b b, one more 0 is there. Okay, 0 0 bb. Now instead of b I can substitute, because you have two zeros then 1, so 0 0 I will substitute 1s for this b, so 1s b. Okay, so again after 1s you can see I need another 1, so I have the next terminal non-terminal symbol is s, so you will go for rule number 1, so you will have 1a b. Now after 0 again I need 0 over here, so a can be substituted with a 0, so I will substitute 0 here, so 0 0 1 1 0. The next symbol is b, so what you need is 1, so you will substitute 1s over here, so 0 0 1 1 0 1s, you will substitute 1s. Okay, so when 1s is substituted you can have, so you have already done, so you need 0 1, so now for this yes, so what is the remaining term we have to have is 0 1. So what I do is I will substitute 0 0 1 1 0 1 0 b. Okay, so instead of b I can substitute 1. Finally I can substitute 0 0 1 1 0 1 0 1. My string is accepted. So now we'll see the final example. This is the last example for today's topic. We are going to use epsilon with it. So let us do for the string 0 0 0 1 0 1. So this is LMD. We are going to do with LMD. So our starting symbol is s tends to a1b. Okay, so now leftmost, so instead of a I will substitute 0a, so 0a1b. Again I need two zeros, so I will substitute again for a alone, so 0 0 a1b. Now I need 0 1 over here, so now this another a is here, so I don't want this, so I can substitute epsilon over here, so you will have 0 1 b here. Now for this b I can substitute 0b, so substitute 0b here, and for this b I can again substitute 1b to get the final one, because we have epsilon here, so 0 0 1 0 1b. Then finally you can substitute epsilon, so 0 0 1 0 1 alone. So string is accepted. So this is based on the rule number 2. Again this is rule 2, this is also rule 2, and after that we started substituting rule 3s. So you can verify with this rule 3 and everything. So if you need, you write this rule number. If you are well enough, you don't want to write it. Now we'll go for the RMD. Now we'll check for the RMD using the RMD 0 0 1 0 1. So start with the symbol A1B. So for B I have to substitute. So let me substitute 0B first. So I will substitute A1 0B. Okay. So again I can substitute the third rule again, A101B. Okay, so the end of the string is being getting substituted. So again for this B, I will take this 101 as not a middle string, I will take it as the end of the string. So because the 101 is the end, so you'll have 101 epsilon. Now the next string is to be A, so you can substitute, you can see two zeros are there, so you'll substitute 0A 101. Again for this A you will substitute, so you'll have 0 0 A 101, only A is there, so substitute epsilon, so 0 epsilon 101, finally you will get 0 0 101. So I have given enough examples for derivation using LMD and RMD. So if you need, you can draw the tree for this derivation tree. So I will draw the derivation tree. So A 1 and this is B, and for this B I have substituted 1B again. Okay, for first one is 0B, then again I substituted 1B, then finally epsilon, and for this I have substituted 0A, again I have substituted 0A, then finally I have substituted epsilon. So when you consider the leaf nodes alone, you can see it is 0 0 and it is 1 0. So I made a mistake over here, just let me correct. So this is first substitution is 1 and then substitution is no. It is 0 and 1 only. Actually I missed the middle term over there. So it is 1 0 1. So it has to come in this way. So this is the final example for derivation using LMD and RMD. Today we have seen about context-free grammar, context-free language. So already we have discussed how a grammar is generated from language, how language is generated from grammar, how do we derive it, how do we derive it in LMD fashion and RMD fashion, everything is discussed. So thank you.